So what if we have repeated poles which would give us multiple poles, similar poles? For example, if you have, say, f at s, f at s is equal to some numerator over, say, s minus p raised to 3. So that gives us, that's the same as, see, we have some numerator over s minus p times s minus p times s minus p. So in this case we have multiple, we have poles, but repeated poles. So when we have repeated poles, we have a way to find these functions. So in that case, when we have a function like this, for example, when we have n over s times s raised to minus p, then we will try to decompose this into a over s minus p plus b over s minus p squared plus c over s minus p the whole cubed. So that's how we are going to decompose it. We are not going to use just one s minus p, but s minus p squared, and s minus p cubed. So in that case, the question is, what are the values of an and bn and cn is going to be? So I think it will this will be better if we do it using an example. So as an example, let's take f of s, for example. F of s to be equal to, say, 2 over s cubed plus 12s squared plus 6s. So this is, if we decompose this, or if we rewrite it, it is the same as s multiplied by s squared plus 12s plus 6, right? Yeah, s squared plus 12s plus, let me use 36 here, so that it will be according to our example. So we have s, we have here s plus 6 and s plus 6, right? Because 12 can be decomposed into those two. This is the same as 2s times s plus 6 squared. So in this case, we are going to have a over s plus b over s plus 6 plus c over s plus 6 the whole squared. So in such cases, we have to use, now for this and this, we don't have any problem. So as we know, a is equal to, in this case, we just multiply f of s by s and take s for 0 because it's a different pole. And for the square, we don't have any problem too, because for the square, we are going to use the same thing. For c, we just multiply f of s by s plus 6 the whole squared and solve for s equal to minus 6. So if we do that, that would give us c. The problem is for b. So in order to find for b, what we are going to use is a differentiation. So we are going to differentiate that value, that f of s. So in order to find for b, we have a d per ds of s plus 6 the whole squared multiplied by that 2 or f of s and solve it for s equal to minus 6. Because it is 1 lesser in degrees, we are going to differentiate that. So that would give us what? D per ds of, and that would cancel, it would give us what? 2 over s, right? At s equal to minus 6. I hope you have learned this in your differentiation class. So d per ds of that is going to be 2 raised to 2 over s squared, which is minus, and we are going to solve that for s equal to minus 6. Ultimately, it should give us 1 over 18. which means f of s, which is represented as 2 over s cubed plus 12s squared plus 36s, is going to be rewritten as a. So if we solve for a, I have found a to be 1 over 18, and c, which is for the square, is having minus 1 over 3, and b is going to have that. So if we have that, we have 1 over 18 for a, so I have 1 over 18 multiplied by 1 over s, plus for b I have minus 1 over 18 multiplied by 1 over s plus 6, right? And then for c I have minus 1 over 3 multiplied by c is 1 over s plus 6 the whole squared. So once we find that, then solving for the respective Laplace transform is not going to be a problem, because in this case we have that part. You remember we had t, the Laplace transform of, so first if we do that, if we do this, it would give us 1 over 18 u at t minus, that one would give us 1 over 18 e raised to minus 6t u at t minus, the last one would give us 1 over 3 s plus 6 squared, because it is squared. You remember for t we have 1 over s squared, and for e raised to minus 8t we have 1 over s plus a. So when we combine that, we will see that property later. We have t e raised to minus 6t u at t. So that would be the Laplace transform. We are going to see a lot more about that, but the main important thing here is for distinct poles, we don't have any problem here. When we have distinct poles, we just solve for the numerator of each partial fraction. When we have similar poles, then we would decompose that and solve it like this. So in this case, for example, to solve for a, we are going to have a is equal to the d square but over ds squared, d per ds squared of, or because this is 2 degrees less than its original, we are going to derivate that twice and multiply that by s minus p the whole cubed and solve it for s equal to p. And for b, we are going to take just d per ds of f of s, multiply that by s minus p the whole cube. And for c, we will just multiply f at s by s minus p the whole cubed and solve for s equal to p. So for this one we are not going to integrate because it has the same degree. For this one we are going to integrate once. For this one you are going to integrate. For this you are going to integrate twice. So that will be on repeated poles, and next time we are going to see properties of Laplace transform. Thank you.